No, no, no. Okay. All right, so we're going to get into equilibrium and Le Chatelier's principle. And today we're really just going to be talking about the forward and reverse reactions. Oh, this chair. Okay. And so this idea of equilibrium, it's really this competition of the forward and reverse reaction. So we say that equilibrium is achieved when the reaction and its reverse reaction proceed at the same rate. So there's always activity going on. Reactants are always becoming products, and products are becoming reactants at the same rate. And it's temperature dependent. So if we look at this reaction, you could think about this as we've got N2O4 that's spontaneously breaking apart into two smaller molecules that happen to be brown in color. So the NO2 is brown. And if you cool it down, then those there's less kinetic energy, and those molecules can stick to each other and make an N2O4. If you heat it up, the kinetic energy in that molecule will cause it to break apart. So higher temperature ought to have more of the smaller molecule, and lower temperature ought to have more of the single molecule, and that's what we see. Because the smaller molecule is a brown color, at room temperature we see this nice brown gas in here, and we're just looking at the little small molecules are the brown colored ones. Then we go to ice water, and you see it's pale. It's not clear, but it's paler. We have less of the smaller molecules. We get to dry ice temperature, it's almost all N2O4, and there's very little of the small molecules. All three of these are at equilibrium. It's just that their equilibrium constant is different. It's temperature dependent. Okay. So this is what's going on when we start the reaction. Let's say we start the reaction with N2O4, and we have very little of the NO2. Because we have so much N2O4, some of it's going to break apart, and that's going to create NO2. And then it just keeps breaking apart until we have so much NO2 that it starts to recombine and making the N2O4. Since we have so much more of it, it's more likely with this concentration to form more N2O4 than the N2O4 is to break apart. And so eventually these two rates are equal. And so we end up with this equilibrium concentration of both. Now it appears that the amount remains constant. So notice how it looks like the NO2 has stopped changing and the N2O4 has stopped changing. And so the amounts are constant at equilibrium, but individual molecules are constantly changing back and forth. So if you could see down at the level, you would see an N2O4 bust apart, and then you might see two NO2s hit each other and get stuck. And that's happening, and it's happening quite frequently. Maybe, let's see, a billion is 10 to the 9th, so a trillion, 10 to the 12th. So probably 10 trillion times a second. That's at 1 atmosphere, that's about how often a gas collides with itself. It's 10 trillion times every second. That's a lot of collisions. That's a lot of things happening back and forth. And so this is two plots here. The left is showing concentration over time, and the right is showing those rates. Okay, and so as we have a high concentration of the N2O4, the rate is high, but as that concentration starts to fall, the rate slows down. And as we have very little NO2 at the beginning, then the reaction rate's really low. But as we raise a little bit of that NO2, it's a second order reaction, so it goes even faster, a steeper slope. It rises up really quick. And so then these eventually reach the same rate, and that's the equilibrium condition. Okay. So let's think about this equilibrium constant. The forward reaction is written here, N2O4 breaking apart to make NO2. And the reverse reaction is written over here, the NO2 combining to make N2O4. Look at the assumptions that we're making on the rate law. we're assuming, since there's a one of these molecules, that it's K times the concentration of N2O4 to the first power. So that's the assumption that we were just told in the last chapter not to make. Remember the can't tell answers? That was the thing we said we can't tell by looking at that reaction. Same over here. We see this 2 right here. We're assuming that means it's second order in NO2, okay? And so these are shaky assumptions, but for equilibrium, it works really well, okay? So what we were doing in the last time with kinetics, we were saying this is the rate law. If I know the rate law, I can predict the future, right? Well, we're really going to, in equilibrium, we're going to do a ratio, and the errors kind of cancel out. So here's the equilibrium constant. If, by definition, at equilibrium, the forward rate and the reverse rate equal each other, okay, so our rate with the lower f, that's a forward rate, and that's equal to the reverse rate. So we take those rate laws, those assumptions that we had before, and put them equal to each other. And I said each one of those individual assumptions was shaky, but when combined in this way, they're pretty good, okay? Because if one of them is wrong on the left side, the other one's just as wrong on the right side. And so the wrongness of that assumption is canceling out to some degree. And it even cancels out more when we rewrite it like this. So we take the ratio of the concentrations. So we just moved this N2O4 over onto the right, and the reverse reaction rate constant over to the left. And we get this ratio, and that ratio is the equilibrium constant. And so we determine these equilibrium constants by experiment. So if that assumption is off a little bit, it just changes this value of this experimental constant, okay? So it's sort of all of the uncertainties are lumped over into this constant that we determine experimentally. So we can make the assumption with the concentrations, and then the constant kind of fixes that. So if you're really like a concrete person and they were bothered, last chapter you told me not to do this, this chapter you're telling me to do this, it's because we're taking the ratio, and the constant absorbs that mistake, if you will, okay? So this is how you write out the equilibrium constant expression. So we just look at this reaction, we take the products over the reactants, and so it's the concentration of NO2, and then this 2 right here becomes an exponent, okay, divided by the concentrations of the reactants. So that we can generalize this for any reaction. So if we have A moles of A and B moles of B, producing C moles of C and D moles of D, this would be the general concentration reaction rate constant. I mean, not rate constant, but equilibrium constant. And it's products over reactants, taking into account those exponents, using the coefficients for the exponents. We could do this with yes. Yes, the coefficient becomes the exponent. Yeah, there's no funny business there. So whatever that coefficient is, if it's, like I said, 6 moles of water, then it's concentration of water to the sixth power. We could do this with pressures. So again, if everything's gaseous, if you're looking up here, we notice these are gaseous components. We could write it in terms of partial pressures. So the partial pressure of C raised to the C power, the partial pressure of D raised to the D power. So it's the same thing, but instead of the square brackets, which mean concentration, it's P for partial pressure. Now, how are these related? Well, we know that PV equals nRT, and we could find a molarity, right? Moles per liter of solution by rearranging that. So this piece right here is kind of like the concentration piece, right? And so we just have a lot of extra RTs on there. For every species, we have the concentration times RT for those gaseous components. And so plugging this expression into the pressure equation for each substance, we end up with this equilibrium constant where it's written all in partial pressures is equal to the concentration equilibrium constant times RT raised to this delta N. And that delta N is just the difference in gases in the reactants and products. So this is how you can relate the concentration equilibrium constant to the pressure or partial pressure equilibrium constant. So let's look at this thing called the reaction quotient. Notice the reaction quotient, Q, yes. Yeah. So it's that number of moles of gas in the products minus the number of moles of gas in the reactants. Okay. And then I want to try to catch up because we passed the exams out. And so we're going quick, but you have the video if you miss anything. So notice Q looks just like K. But Q can be calculated at any time. K is specifically for equilibrium. So when it's at equilibrium, you get the equilibrium constant values. But if you're, say, at the beginning of the reaction and you have all reactants and no products, then you have Q, the reaction quotient, okay? And so if we look at this, if we have this reaction here, SO2 plus oxygen gives SO3, and at the beginning of the reaction, we have all reactants, right? The oxygen concentration is here, the SO2 concentration is here, and we have 0 products. So what is the reaction quotient? It looks just like the equilibrium constant, but you put in the actual amounts at that point in time. Okay, and so we have some value. We don't really care what X is, but we have 0 products. And so it doesn't matter what the denominator is. We know we have 0 on top. And so Q is actually 0. When we have all reactants and no products, Q is 0. And if Q is less than K, the reaction is going to go forward because it's got to produce some products. Let's look at this situation. Yeah, Q changes and becomes K at equilibrium. Because we could calculate Q right here. You know, we could have this many products and this many reactants, and so we could get Q here. And notice we don't have enough products and we have more than enough reactants, and so Q is still less than K. And then when equilibrium is reached, Q is equal to K.
Can you explain what Q is again?
It's just another letter to use other than K, because K is specific to equilibrium. So we can't call it K. So we got to call it something else. And since it's a ratio, a quotient, they call it the reaction quotient. So there's nothing really magical about it. It's just the K calculation, but you can't say K because K is specific for equilibrium. So we got to call it something else. So we'll call it Q. Over here, we have at the beginning of the reaction all products and no reactants. And so we're dividing by 0 now. Since reactants are 0, we're dividing by 0. And so we have Q as infinity. And infinity is greater than any other number. And so Q is much, much greater than K. And even here, we don't have enough reactants. We've got too much product. Q is still greater than K. Notice it's only 1 greater than. Oh, sorry, I said greater and wrote lesser. Okay, Q is still greater than K, but here Q is equal to K. So you see how it can decrease, it can increase, but when it equals K, you're at equilibrium. Yes. Because we have all products and 0 reactants, and so it's infinity.
But does it really? Do you have to have the double greater than?
That's just I've seen it a lot, and when people try to say it's much greater, yeah, so they're just saying greater. Yeah, it's much greater. Yeah, so that's just a shorthand for saying much less or much greater. You just put 2 of them. Yeah, good question. And so Q will change and become K at equilibrium. So same kind of thing. But we can look at this and we can see that when Q is less than K, so this is a nice, you can put a star by this to kind of give you an idea of how to think about this. By definition, when Q equals K, the system is at equilibrium. When Q is less than K, there's too many reactants, and the reaction will move forward to form products, right? So the reaction forms products when Q is less than K. If Q is greater than K, so like over in this case, you see Q is higher than K, this reaction is going to run backwards. So we have too many products, not enough reactants, and so it's going to run backwards until it reaches equilibrium. And that's totally legit, right? Because we have a double-headed arrow. These reactants and products can go backward and forth. So if we have too many products, it's going to run backwards until we get to equilibrium.
So is that, I was going to say, is that Le Chatelier's?
Yeah, and so this is the roots of Le Chatelier's principle. And Le Chatelier's principle says when you're at equilibrium and you push on the reaction, like you add more products, it'll run backwards. Add more reactants, it'll run forwards. So Le Chatelier's principle is how the system reacts. But this is the basis of it. If Q is greater than K, then it's going to run backwards. If Q is less than K, it'll run forwards. So in Le Chatelier's principle, if you have a system that's currently at equilibrium and you change it, you break the equilibrium, you can look at Q now and see which direction it's going to go. And here's 3 different starting points just to kind of show you that before the reaction and the after the reaction. The equilibrium constant at a temperature, particular temperature, is constant, okay? That's why it's the equilibrium constant. It's right there in the name. So no matter what you start with, if you're at a given temperature, it's going to reach that constant. And this is a ratio. So we can have many different ratios of products to reactants that still give you the same ratio, right? I can have a ratio that equals 2. And that can be 4 divided by 2. That could also be 8 divided by 4. That could be 16 divided by 8. So there's an infinite number of ways to get the ratio 2. So there's an infinite number of amounts of products and reactants that will give you the equilibrium constant. So here's 3. We start with mixture 1. In this particular reaction, we can see the color code here that CO is red and water is blue, and CO2 and hydrogen are green and yellow. So here we're starting with pure reactants, no products. Okay, so no products, that means Q is equal to 0. So that's this particular case, Q is equal to 0. We let the reaction run. Notice that the products have decreased. They went from 0.02 down to 0.01, and we got products. Okay, and the ratio of products over reactants gives us our equilibrium constant. If we started with all products, so we started with CO2 and water and hydrogen, that's again an infinite Q. Look, the products have decreased and the reactants have increased. It ran backwards and produced this. The ratio of products over reactants is our equilibrium constant. So here's another way to achieve the same constant. It's just I had more amounts of everything, and so I've got, like larger numbers divided by larger numbers to give me the same equilibrium constant. Here, just starting at a random mixture that's not at equilibrium, I've got some reactants, I've got some small amounts of products. Q is 0.0045. Compare that to K, which is 0.640. Okay, so Q is less than K. So that means this reaction should go forward to make more products so that Q can creep up until it hits K. And sure enough, we produce more products, reduce the reactants, we end up with K. Okay. So just showing you 3 different ways, you start it with different situations and you end up with the same ratios, different amounts, but same ratios to equal K. Now we get into some ways to manipulate equations and what that does to the equilibrium constant expression. So if we have this reaction, we could write out K, the equilibrium constant. We do some experiments and we discover that it's 0.212. So that is the value of K for this reaction. What if we doubled that reaction? So for stoichiometric reasons, maybe I needed to have some reactions work together, and I ended up with this reaction doubled. So I'm going to multiply everything by 2, and I'm going to get this. So 2 N2O4 gives 4 NO2s. Here's the equilibrium constant expression for that, which if you look at this versus the one above it, it's really the one above it squared. Because we doubled the reaction, we squared the equilibrium constant expression, okay? So if you double the reaction, you square K. If you cut it in half, you're going to take the square root, okay? So this would be the second reaction would have the equilibrium constant value of 0.212 squared, or 0.0449. Okay. So that would be the equilibrium constant for this one right here. Okay.
So, do the exponents attached to the molarity, to the concentration, is that still like for the order?
Yeah. So, but it would be like the forward rate and the reverse rate. But we're out of kinetics, so we're not talking about individual reaction rates. We're talking about the equilibrium, which is the forward and reverse rates working against each other. Yeah, yeah. But you would say the forward rate is fourth order of NO2, and the reverse is second order in N2O4 for this reaction with those doubled exponents. Yeah. Okay. Let's look at another one. What if we had the situation where we're going to have two reactions combined? So we have this reaction, and then it feeds into the next reaction. Notice the product of this reaction is a reactant of the next reaction, and it's going to produce new products. So this reaction equilibrium constant is written like this, right? Products over reactants, nitrogen, oxygen squared over NO2 squared. And if I'm going to combine these two, then it's the product of these equilibrium constant expressions. And you can look at this and you can say, well, this will simplify, right? I've got this in the denominator. I've got that in the numerator. They cancel out. And so K3 is the overall products divided by the initial reactants. How does that look over here? You know, if we were to take this and just add these two equations, then we would end up with this equation down here. We would have the N2O4, and you might have the plus 2NO2 on this side. And then over here we have the 2NO2 on this side, plus the N2 plus the O2. Since this is on the same on both sides of the reaction, just like in math, we can subtract that from both sides and it disappears. Okay, so these being on both sides of the reaction will actually cancel each other out. It's like they're not even there. They don't participate. They were a reactant, they were a product, they were unchanged. And so they're irrelevant. So this is the net reaction down here. And this is the net equilibrium constant expression. So let me just say added produces multiplied. You see what I'm saying? We add the reactions, we multiply the K's. Okay. Let's talk about something that's a little strange. Here's an aqueous reaction that involves water. So over here we have the species that has water as a part of this compound. That whole thing is aqueous. But when it breaks apart, we have liquid water. And these square brackets mean concentration. And that would be moles of solute in the liters of solution. Okay, this in aqueous solution, this is the solvent. okay? This is going to be a constant value. These aqueous values can change. We have different molarities for all of these things. But for water, it's a constant value. Water has so many moles per liter of water, and you can't make water more concentrated in water or less concentrated in water. And so since it's a constant, it gets lumped over in here. So the liquid species, like water, liquid water, are actually over in the constant part, and we don't include it in the expression. So this is the equilibrium constant for this reaction. Notice there's no water in this expression. There's no square bracket water because of this right here, because it says liquid water. Okay. You do the same thing for solids. Let's say in this reaction, maybe we had a cobalt solid and it was becoming aqueous, and you would delete the solid from that expression as well. Okay. So here's a solid one. You might want to do reactants over products, right? So the reactants are the concentration of lead, the concentration of chloride squared, but notice this is a solid. And so the concentration of the solid in the solid is going to be constant. And so it gets stuck over here in the numerical value of that constant, and we just have the things that can change. So the concentrations of these aqueous species can change, and so the things that change are on the right, the things that are constant are on the left. Okay. So this is called the solubility product constant, because whenever you have this, species like lead chloride, which is a solid, very little of it dissolves in water, but you have the product of those concentrations equals this constant. So we call it the product constant. It's a product of the species that change. So let's practice. So don't just copy these down. Look at the reaction in your notes and try to figure out what you would have. So in this case, we have gases. You could write those as partial pressures. And so we have the partial pressure of CO2, which is the product, squared, because it's 2, divided by the partial pressure of CO, squared, because there's 2 of them. And notice the solids are not there. So we don't include the solids in the expression. What about this one? Here, solids. We have solid zinc and solid copper. We ignore those. We have zinc concentration in the numerator, copper concentration in the denominator. This one is really strange. Everything's a solid but the CO2. Okay. And so we just have this equilibrium constant in terms of pressure is just the partial pressure of CO2. And as long as you have calcium oxide in equilibrium with calcium carbonate, you're going to have a constant pressure of CO2. It'll be temperature dependent, but at a given temperature, you'll have a constant pressure of CO2. So thanks for your attention. We made it in time. Yeah, question? Oh, yeah. Yeah.
Okay, I really need you to pray for me in this class.